Hello students, I am Isha Medirata. In today's video, we will be discussing what is a dielectric, types of dielectrics, and we will also discuss some basic terms which are related to dielectrics. So let's start. Let's see what a dielectric is. So in electromagnetism, we say that a dielectric is an electrical insulator which is polarized when you apply an electric field. Some examples of dielectrics are ceramics, rubber, plastic, wood, etc. Let's have a better understanding of how electric field polarizes a dielectric, or what happens to a dielectric material when an electric field is applied. So in this diagram, you can see that on the left hand side, when there is no electric field, you see that the charges are randomly oriented, right? On the right hand side, we see that there is an electric field applied in the right direction. Now what happens due to this electric field? Now we know that whenever electric field is applied, all the positive charges will try to move in the direction of electric field, but the negative charges will try to move away from the electric field. And you can see in this second diagram, how are the charges oriented? The charges are oriented in such a way that the positives move towards the negative plate and the negative charges try to align or orient themselves towards the positive plate. So this is how we say that dipoles are created. Now what do you mean by a dipole? A dipole is nothing but a pair of positive and negative charges which are separated by a small distance. So if there is an atom, you apply electric field, the electrons will try to oppose the electric field. In that particular condition, I would say that there is a space or a distance created between the positive and negative charges, and thus I say that a dipole is induced or a dipole is created. So this is how a dielectric material polarizes, and I would say that dielectric polarizes in the presence of electric field. Then we have polarization. Now what do you mean by the word polarization? It is nothing but inducing dipoles in a dielectric when you apply an electric field to it. So I have applied an electric field. What happens? The charges reorient them according to the applied electric field, and this is how I say that dipoles are induced or dipoles are created in a dielectric material. So this process is what is known as polarization. Let's move ahead. This is a topic which will explain you the basic types of dielectric materials. The first one of them is known as a non-polar dielectric. Now what do you mean by a non-polar dielectric? Non-polar dielectric materials are materials in which no permanent dipoles exist in the absence of electric field. That means there are no dipoles if there is no electric field, and that is quite obvious as per the previous explanation. Let's understand with the help of a diagram what exactly the statement means. So in the left hand side, you see that there is no electric field, E is equals to 0, and the charges are stable as it is. Now what happens when an electric field is applied? So you can see that the charges have reoriented according to the applied electric field. So there is a difference or a distance created between the positive and negative charges, and this is how we say that dipoles are induced. So these are the materials which have dipoles only when electric field is applied. Let's have a look at some of the examples. Some of the examples of such materials which are non-polar are hydrogen, nitrogen, oxygen, carbon dioxide, and CH4, that is methane. So these are the materials which do not have dipoles when there is no electric field. Now let's have a look at the other type of dielectric material, the other category, which is known as a polar dielectric. These materials are very commonly known as polar molecules also. Now what do you mean by a polar dielectric? So polar dielectric is a material in which permanent dipoles exist even if there is no electric field applied. So even if there is an absence of electric field, these are the materials which have permanent dipoles. Let's understand with the help of a diagram. So in this diagram, you can see that on the left hand portion, that is on the left hand side, you can see there are charges. There are dipoles already, but all the dipoles are randomly oriented, right? So what will happen if all the dipoles are random? The net dipole moment would be 0. But what happens when you apply electric fields? So in the second diagram, you can see that an electric field is applied and you can see that all the dipoles have reoriented or aligned them with respect to electric field. Clear? So when electric field is not 0, I would say the dipole moment is also not 0 because the dipoles are no more random. Clear? Let's have a look at some of the examples. Some of the examples of such polar molecules or polar dielectrics. You have H2O, that is water. You have CO, carbon monoxide, and HCl, that is hydrochloric acid. So these are some of the examples of polar dielectrics or polar molecules. Let's move ahead and start with some of the basic terms which are related to dielectrics. So starting with the first term, we have relative permittivity, which is also known as the dielectric constant. Relative permittivity is denoted by the term epsilon r. It is defined as the ratio of permittivity of a medium with respect to permittivity of free space. What is permittivity of a medium? It is denoted by epsilon, and permittivity of free space is denoted by epsilon naught. So we have, as I said, it is known as a dielectric constant, and the equation is epsilon r is equals to epsilon by epsilon naught. This is a ratio of two different types of permittivity. So this is a dimensionless quantity or a unitless quantity. It doesn't have any unit. Next we have electric field. What do you mean by electric field? Now, electric field can be explained by different methods, but what we are concerned in this particular topic. So electric field is defined as the force which acts on a unit positive charge placed at that point. What does that mean? Suppose you have a test charge, say a positive charge. You bring one more positive charge close to it. What will happen to this moving charge? It will get repelled because this test charge is positive. But instead of a positive charge, suppose I bring a negative charge close to this test charge, it will get attracted. Did you notice in both the cases, there is a force attracted. When the charges are like, they will be repelled. When the charges are oppositely charged, they will be attracted. So I can say that the unit test charge has applied a force on the other charge. Why? Because there is electric field or there is the effect of this charge surrounding the test charge. This is what is known as electric field. Clear? So you can see in this diagram that the arrows indicate the actual effect of the charge in between. You can also understand with the help of this. This indicates, the second animation tells you what happens when there are like charges. You can see these are getting repelled. But what happens when the charges are like, they are getting attracted. So this is because of the force exerted by the test charge. It is defined as F by Q. It has two units. It can be written as Newton per Coulomb or it can be written as Volt per meter. The relation between these two units is 1 Newton per Coulomb is equals to 1 Volt per meter. Moving on to the next term, we have electric flux, that is phi. Now, electric flux is actually imaginary. They are imaginary lines with respect to a dielectric. It is defined as the number of lines that pass through the surface placed in a vector field. Mathematically, the product of surface area, component of electric field, which is normal to the surface. So, it is the product of surface area and the component of electric field, which is normal to the surface. Normal, or you say perpendicular to the surface. And it is defined as phi is equals to E into ds, where ds is a component of surface area, right? Let's see with the help of a diagram what is electric flux. So you can see that it is a product of E and A, and we denote it as EA cos theta. You can see the imaginary lines which are indicated by the dotted lines, which are always normal to the surface. So this is what electric flux is. Moving ahead, we have electric flux density. Now, what is electric flux density? It is also denoted as D, capital D. It is the flux passing per unit area of a section which is held normal to the direction of flux. It is also known as the displacement vector, defined as D is equals to epsilon into E. What is epsilon? Epsilon is known as permittivity of the medium. So I can also write this equation as D is equals to epsilon naught epsilon R into E. Let's understand this with the help of a diagram, and before that I can also write D as phi by A, that is flux per unit area. Let's understand with the help of a diagram. So in the left hand side you can see that there is no displacement, or the electric flux density is 0. Why? Because no electric field is applied. Now on the right hand side of the diagram you can see that there is an electric field applied in this particular condition, and we have D is equals to epsilon into E. What is the difference between these two diagrams? The second diagram shows you that dipoles have been created. That means the charges have moved, or I say that charges have been displaced. So there is a flux induced, and with respect to particular area, we say that there is displacement or electric flux density. Next we have a term called polarization. So at the beginning of the lecture I told you that dipoles are induced in a dielectric when electric field is applied, right? So this process of inducing or creating dipoles is what is known as polarization. So this gives a broad idea of what polarization is. It measures the extent of polarization in a dielectric material. It's a vector quantity. This is how it can be represented. So in the left diagram you can see that all the charges are present in the dielectric material as it is when there is no electric field applied. But on the right hand side of the diagram you can see that one of the plate is positive, the other plate is negative. How are the charges reoriented? The negatives move towards the positive plate and the positives move towards the negative plate, thus creating dipoles, and hence we say that the material is polarized. This is the meaning of polarization vector. It is defined as induced dipole moment per unit volume. You can say n nu, or it is defined as the surface charge per unit area. What are the charges developed on the surface per unit area? Because those charges per unit area are a result of the dipoles which have been created. So you can say it is equal to n into mu, where mu is the net dipole moment and n is the number of charges, or you can say P is equals to Q by A, where Q is the surface charge and A is the cross-sectional area. Then we have a term called susceptibility. What do you mean in general by susceptibility? Do you know what is immunity? If you resist something, you say that you have a high immunity. So susceptibility is known as the opposite of immunity. So if you have a dielectric material and you apply electric field to it, if it easily polarizes, that means if easily the dipoles are created in the dielectric, I will say the susceptibility of the material is high. Clear? It is a dimensionless proportionality constant which indicates degree of polarization of a dielectric material in response to the applied electric field. So what exactly happens inside a dielectric, to what extent it polarizes with respect to applied field, this is what is termed as its susceptibility. It is denoted as chi E. It is a dimensionless quantity. It is defined as the ratio of polarization with respect to net electric field, right? And it is defined as chi E is equals to P upon epsilon naught into E, where P is the polarization, epsilon naught is known as the permittivity of free space, and E is the applied electric field. Then let us derive a small relation between polarization, that is P, susceptibility, that is chi E, and the dielectric constant. So in this diagram you can see that there are two plates. The plates are in such a way that upper plate is positively charged and lower plate is negatively charged. So I say that there is an electric field applied in a direction upward, that is E naught. Now because of the applied electric field, inside the dielectric slab also there is an electric field induced. Why? Because all the negative charges of the dielectric slab try to move towards the positive plate, and all the positive charges of the dielectric material try to move towards the negative plate. So if applied field is in upward direction, the induced electric field in the dielectric will be in the downward direction. I hope that is clear. Now let's see. This is a parallel plate capacitor in which electric field E0 is applied in the upward direction. And if I say that sigma is the charge density, the surface charge density due to this applied electric field, then from Gauss's law, I can say that electric field E0 is equals to sigma by epsilon naught. Clear? Similarly, I have polarization created in the dielectric due to the applied electric field. That is the only reason I get electric field induced in the dielectric also. So I say that the resultant field E will be applied E0 minus induced E1. So this gives me the resultant field due to the applied electric field. So I can say that there is a surface charge density at the surface of the dielectric slab also. This I denote it as sigma S. So E1, that is the induced field, is equals to sigma S by epsilon naught. So I got two equations, one with respect to E0, the other with respect to E1. Hence I can say that from the equations 1 and 2, I have epsilon naught into E is equals to sigma minus sigma S. What have I done? I have substituted the equation of E0 and E1 in the above equation, that is E equal to E0 minus E1. So I get epsilon naught E is equals to sigma minus sigma S. But now, sigma S is equals to P. So the surface charge on the dielectric is due to polarization, and that is what is known as the surface charge density of the dielectric, which is known as polarization P. And due to the applied field, the flux, due to the flux created, we have displacement D is equals to sigma. Or I can say the surface charge density of the dielectric slab is sigma S, and the surface charge density at the metal plates is D. That is displacement vector, or you can say the electric field density. Clear? So now what do I do is, I just replace the values of sigma and sigma S, and I get a modified equation as epsilon E is equals to D minus P. Now, what do we have? From electrostatics, that is from the definition of displacement vector, we can say that D is equals to epsilon naught epsilon R into E. So I just substitute this equation in the above equation and I get epsilon naught E is equals to epsilon naught epsilon R E plus P. This is what I get. So I have just substituted the above equation. Now what do I do is I substitute the equation of D in the above equation and I just rearrange. So I get epsilon naught epsilon R E is equals to epsilon E plus P. And then I just rearrange the terms again and I have epsilon naught E into bracket epsilon R minus 1 is equal to P. We know that P upon epsilon naught E, that is polarization with respect to the net electric field, is known as susceptibility, and hence we get the equation chi E is equals to epsilon R minus 1. So this equation is the relation between dielectric constant epsilon R and electric susceptibility chi E. So we have derived the equation chi E is equals to epsilon R minus 1. Lastly, we have a term called polarisability, which is denoted by alpha. It is a property of an individual atom or molecule. It's basically a proportionality constant, because we know that there is polarization with respect to applied electric field. So I can say that the dipole moment is somewhere related to the electric field applied, or I would say that the dipole moment is proportional to the applied electric field. Clear? And this proportionality constant is nothing but alpha. So let's see, we have mu, that is dipole moment is proportional to E. If we remove the proportionality sign, we introduce a constant alpha, which is known as mu is equals to alpha E, where alpha is known as the polarizability of the material. It is a proportionality constant having the unit farad meter square. Clear? So today we have discussed what is a dielectric material. We have seen the two basic types of dielectric materials, that is polar and non-polar dielectrics, and we have discussed some basic terms related to dielectrics. Hope you have understood all the topics I discussed today very well. Thank you.